Hello everyone. Today we will be discussing the competitive inhibition derivation. The competitive inhibition kinetic reaction is going to be represented by the below chemical equation. A quick review of competitive inhibition is when the enzyme can bind to either the inhibitor present to form an enzyme inhibitor complex or can bind to the substrate to form an ES complex, which can eventually form to the end product of the enzyme and the product. Now, we can also see that as the same with the enzyme substrate complex, we have this K3 rate parameter for the enzyme binding to the inhibitor. And we also have the K-3 rate parameter to show the rate that the inhibitor dissociates from the enzyme. So now we are going to be introducing another important component of modeling that we previously didn't introduce, because this value is only important when we're dealing with reactions that have an inhibitor within them. Similar to how we had the Michaelis constant that measured the substrate's affinity to binding and staying bound to the enzyme based on the rate parameters, we also have a constant called the inhibition constant that measures the inhibitor's affinity to bind and stay bound to the enzyme. Similar to the Michaelis constant, the measure of this constant is through dividing the rate that the enzyme dissociates from the inhibitor over the rate that the enzyme associates with the inhibitor. Furthermore, it is also an intrinsic value of the inhibitor and enzyme. Thus, based on our schematic, it would be represented as the K-3 rate parameter over the K3 rate parameter. Now that we have talked a little bit about the inhibitor constant, we can move on to two main tips to have when deriving these equations. The first is to ensure that you always try and isolate the inhibitor constant and Michaelis constants as soon as possible. These are really important to isolate because it's really difficult deriving the equations if we have all these rate parameters floating around. A second main tip is to always try and find a way to isolate the enzyme substrate concentration. This is because, as we saw in our last derivation, our goal with these equations is to represent the rate of product formation in terms of enzyme concentration, substrate concentration, and the Michaelis constant and inhibitor constant. So our goal should be to always try and isolate the enzyme substrate concentration in terms of these four terms. Now we will be switching to the screencast and beginning to derive our competitive inhibition kinetics. Hello, this is going to be the screencast section of the competitive inhibition derivation. So the first thing that we're going to be doing is we're going to be talking about some of our previous assumptions. So we talked about how we stated that the enzyme concentration change over time is going to be equal to 0 due to the fact that an enzyme is not modified or changed during an enzyme substrate reaction. We're also going to state that the enzyme substrate complex concentration over time is also going to be equal to 0, as well as the enzyme inhibitor complex concentration change over time is going to be equal to 0. And these two are going to be because of our rapid equilibrium assumption. So now what we're going to be doing is we're going to be using the law of mass action to firstly derive the changes in enzyme substrate complex concentration over time. And we're also going to be doing this for the changes in the enzyme inhibitor complex concentration over time, and finally the changes in product concentration over time. So for enzyme substrate complex concentration changes over time, we're going to be doing the rate of association, which is the enzyme concentration times the substrate concentration times the K1 parameter. We're going to be subtracting these by the rate of dissociation, so it's going to be the enzyme substrate complex concentration times the K-1 rate parameter, as well as the enzyme substrate complex concentration times the K2 rate parameter. For the enzyme inhibitor complex concentration changes over time, we're going to be doing the same process, and the rate of association is going to be the enzyme concentration times the inhibitor concentration times the K3 rate parameter, subtracted from the rate of dissociation, which is the enzyme inhibitor complex concentration, multiplied by the K-3 rate parameter. Finally, we have the changes in product concentration over time, and this should look familiar, and it's going to be the enzyme substrate complex times complex concentration times the K2 rate parameter. And because there's no rate of dissociation, there's only this arrow pointing towards it, so there's no rate of dissociation that we have to derive. And finally, this is just a reminder, our enzyme total concentration is going to be the enzyme concentration plus the enzyme substrate complex concentration plus the enzyme inhibitor complex concentration. And this is going to be what we're going to be trying to use so that we can plug all these equations back into this equation, and so that we can model the rate of product concentration changes over time in terms of the Ki value, the Km value, substrate concentration, enzyme concentration, and inhibitor concentration. So let's begin this process. So the first thing that we're going to be doing is we're going to be taking our assumption that the enzyme substrate complex concentration over time is going to be equal to 0, which is going to be equal to what we derive from the law of mass action. And so what this means is that the rate of association is going to be equal to the rate of dissociation. And so, as we previously mentioned, we're going to be trying to isolate the enzyme concentration in terms of the enzyme substrate complex, so we can plug it back into this ET, enzyme total concentration equation located right here. So what we're going to be doing is dividing both sides of this equation by the substrate concentration times the K1 rate parameter. And so what this is going to be equal to is we're going to firstly try and isolate this Michaelis constant right here. So this is going to right here be the Michaelis constant. So we're going to simplify this and make the enzyme concentration equal to the enzyme substrate concentration times the Michaelis constant over the substrate concentration. So now we have this first value that we can plug in to the enzyme total concentration. So this was our previous equation, but now that we've found the enzyme concentration in terms of ES, we can now make it so that the total enzyme concentration is going to be equal to the enzyme substrate complex concentration plus the enzyme inhibitor complex concentration times the enzyme substrate complex concentration times the Michaelis constant over the substrate concentration. So now what we need to do is we need to make this enzyme inhibitor complex concentration in terms of the enzyme substrate complex concentration. So we're going to be taking this equation that we previously derived from the law of mass action, and we're going to be again using our rapid equilibrium assumption and making this equal to 0. So this also further means that the rate of association is going to be equal to the rate of dissociation for the enzyme inhibitor complex. So what we're going to be now doing is taking what we found from before for the enzyme concentration and plugging it into this enzyme concentration. So now we have the inhibitor concentration times the K3 rate parameter multiplied by the enzyme substrate complex concentration times the Michaelis constant over the substrate concentration. And this is going to be equal to the enzyme inhibitor complex concentration times the K-3 rate parameter. So we're going to be dividing both sides of these by the K-3 rate parameter, and we're going to be able to isolate 1 over Ki. So now we have the enzyme inhibitor complex concentration is going to be equal to the inhibitor concentration times the enzyme substrate concentration times the Michaelis constant over the substrate concentration times the inhibitor constant. So now what we're going to be doing is we're going to be we found the enzyme inhibitor complex concentration in terms of ES. So now we can plug this back into the enzyme total concentration equation. So we're going to be, the total enzyme concentration is going to be ES plus the enzyme substrate concentration times the Michaelis constant over the substrate concentration plus this value we just derived. So I'm just going to be copying and dragging this over here. So now what we can do is we can isolate the enzyme substrate complex concentration. So this will be the enzyme substrate complex concentration multiplied by 1 plus the Michaelis constant over the substrate concentration plus the inhibitor concentration times the Michaelis constant over the substrate concentration times the inhibitor constant. And finally, what we're going to be doing is we're going to be making this in terms of an enzyme substrate complex concentration, because again, we want to plug this back into this equation right here. So how we can do this is we divide both sides of this equation by this right here. So it's going to be equal to the enzyme substrate complex concentration is equal to the total enzyme concentration divided by 1 plus the Michaelis constant over the substrate concentration plus the inhibitor concentration times the Michaelis constant over the substrate concentration times the inhibition constant. So now what we're going to be doing is putting this back in. So we can make dp dt equal to this right here multiplied by the K2 rate parameter. So now we have this, and we can firstly substitute this right here to equal Vmax. So we have the rate of product concentration over time is equal to the Vmax. And we can further simplify some of this down here. So the first thing that we can do is we can take out the Michaelis constant over the substrate concentration and make this 1 plus the inhibitor concentration over the inhibition constant. And then what we can do is multiply both the top numerator and the denominator by substrate concentration. So this is going to make our equation equal to the Vmax multiplied by the substrate concentration over the substrate concentration plus the Michaelis constant times 1 plus the inhibitor concentration over the inhibition constant. And this right here is going to be the final derived version in the most simplest terms. So thank you very much for watching this video, and I hope it was helpful to understand the derivation behind competitive inhibition. Thank you.